we all are here. And it would be great to know about your background before I start, because it would be better way explain to all of you. I hope that most of you are from the polymer background, yes?
Yes.
And a few are related to either tissue engineering or drug delivery system. Very few, I guess. Isn't it? You are tissue engineer. Yes. And very few might be from the 3D printing one, right? So that way I am going to give this talk. So before we enter into this, we should be aware of that how significantly the polymer has influenced our life, isn't it? All the parts have been somehow affected. And here we will specifically talk about our research area, my research area, that is basically dealing with the biopolymers, and that is basically dealing with the natural biopolymers. So the application particularly I am engaged with is the tissue engineering. For those who are actually not aware of the tissue engineering, what exactly it is. So here we are doing some kind of engineering so that we can regenerate the tissues. So whatever the tissues we have, if it is somehow damaged, if it is somehow requiring the replacement, we have to make some kind of engineering so that it can replace the functioning of the natural tissues. So here a simple examples with this you can see here. So here, if something, the cells that we are getting from the body, ultimately it is expanded and we are getting some kind of 3D scaffold support, so that it can be drawn further and it can again, with the help of further cells and growth factors, can implanted into the body itself. So this is the basic idea behind the tissue engineering, and based on the different parts of the body, we have to select the scaffolds, we have to select the growth factor, we have to select the cells. A variety of different components are there. So in the layman language, you can understand that what are the different parts of the tissue engineering, but it is not so easy and so simple as it looks like. The individual steps is very much a determining factor for the success, how exactly it is working in the body. A single step if it is going wrong, a single step when you are selecting the wrong biomaterial, in the single step when you are getting the wrong manufacturing technology, ultimately it is not successful inside the body. So it is very important to select all the steps. So in that particularly, if I am talking about in today's talk, I am basically concerning the scaffold manufacturing technologies and what it is made about. So obviously, in general, we have the two options, that is the natural one and the synthetic one, and philosophically all of you know what is the advantages and disadvantages of the natural and synthetic one. So natural one, obviously it is very close to the nature. So obviously the biomimicking properties of such materials are very much supporting, so that when it is implanted into the body, it will be very much biocompatible. But obviously, as nature demands, the control over its behavior is not there. Right? If you want something that their properties are very much in control, their both architectures are very much in control, it is very difficult when we are dealing with the natural ones. But that is the good part for the synthetic one. The synthetic one, we can control its properties. But again, what is the disadvantages? Biocompatibility is lesser. My research area is basically dealing with the natural biopolymers and the natural biomaterials, including the ceramics. So in that, we are dealing with chitosan, hyaluronic acid, zinc, fibrin, keratin, collagen, hydroxyapatite, tricalcium phosphate. All these basically my lab is dealing with. So here, if we talk the examples of a bone tissue, like what I was telling, that if the tissue is different, the selection is different. The properties that we require is different. So here, with the typical example that I am taking for the bone, ultimately, if we want such materials that can be replaced with the natural tissue, the natural bone, we have to make in such a way that it should be very much supportive for the bone. So here, ultimately, we have to understand that what is the natural architecture of this bone. Naturally, it is made up of collagen and hydroxyapatite, isn't it? But here, what we are doing, we are going for the engineering the things, so that at least if we are not able to improve the property, at least we can mimic the property very closely, isn't it? So our preference will be those materials which can mimic the hydroxyapatite, or that can mimic the collagen, or itself we can use it, right? So for bone tissue engineering, likewise, varieties of requirements are there. Here already we have seen. And now if we want to make the biomaterials, natural biomaterials, so that it can successfully work with the bones, we have to go for the good selection. That is very important, right? So here, in general, we are making whatever the scaffold that is started with the 2D systems. That in the Petri plates, in vitro systems, we can see that, okay, it is very much supporting, the cells are growing in that support system. But inside our body, that 2D doesn't exist. So what we are assuming that when it will enter our body, should work in the same way. Actually, it won't work because our system is 3D. It is not 2D, right? So our effort is that whenever we are going for the study, we are studying in the 3D scaffold systems, whether it is the in vitro study or the in vivo study. And now a new thing has come, that is the 4D technology, right? So now why we are telling that if we want that anything in the 3D, so we have to go for some manufacturing technology that has the control over making in 3D. And the most advanced method is 3D printing that we are dealing with, right? But that is also not most advanced. Now more advanced has come, that is the 4D. What is 4D? That 4D is actually that 3D structures when it is going in another dimensions change due to change in temperature or pH or any other physical or chemical properties when the surrounding is changing. So that way we are playing around with the 3D and the 4D so that it can successfully grow inside the body. So if we talk about the natural and synthetics, these are very general slides which is talking about the biopolymers. Different classes are there, and how among these some could be the biodegradable and some could be non-biodegradable. So if it is non-biodegradable, so obviously nothing is bad in the world, just the thing is that you have to find the right application. So if it is non-biodegradable, so accordingly some applications might be there, but we are not interested. We are interested in the biodegradable systems. Maybe some are degrading very fastly, some are degrading a bit slowly. So likewise, if we talk about the bone, whatever the biodegradation rate should be there, it should not be very fast. It should be minimum 6 months or beyond. But if we talk about the skin, it should not be 6 months, it should be very fast. So likewise, based on the applications, we have to make the right choice, right? Like for example, many research papers has come up for only for the sake that is used for the skin also and for the bone also. Then how we can go for play around with these materials? We have to make some kind of composites. We have to find out something. We have to reinforce it so that it can degrade to very slow rate, so that we can apply for bone. Otherwise, it is for the skin. So ultimately, you have to find out that kind of two approaches are there: top to bottom approach and bottom to top approach in the research. And based on that, accordingly, you can find out that if your application is already defined, accordingly you can go for the selection, manufacturing, application, characterizations, and all those things. That way you can further proceed. So my lab is very much indulged with utilizing the underrated biomaterial, and that is the avian XL membrane. So here in this is the XL membrane, right? And how we are cussing it, here we can see XL membrane powder we are making it. And this XL membrane powder, that is the commercial product named as NEM from the Professor Maxwell Hing, who is my collaborator. So his product is already in the market, and osteoarthritic persons and other persons directly they can take it and get a good relief. But the thing is that if we are using directly the XL membrane in the form of powder, that is not so much absorbable by the body tissues, right? So you have so much of food that you can't digest, obviously the body can utilize it. So we have to process this biomaterial in such a way that it can be utilized by your body, and we have to go for the hydrolysis, right? So for the hydrolysis, there could be many methods. Out of that, one very common method is the enzymatic method that already we have done. So that could be used for the partially hydrolyzed XL membrane that we are making it, and in that part we can go for further applications. Likewise, when we are isolating and we were hydrolyzing it, we can see the clear picture that how the surface is actually devoid of the globular proteins. Now let's go back. I think it is required. So here in this axial membrane, what happens that this axial membrane is basically made of collagen, but in addition to the collagen, many globular proteins are tightly conjugated or packed with it, immobilized with it. That we don't want. Why? Because that structure is only restricting the absorption by the tissues. So what is the solution? One way we have gone for the partial hydrolyzation, so that we can make one part is the collagen solution and another part it could be the ACP, soluble axial membrane protein. Very common it is. You might be seen other parts. So likewise, if we are removing it, likewise you have to analyze the surface property. Why surface property is important and how we are doing it? We go for the contact angle measurement to see that whether it is hydrophilic or hydrophobic. If it is hydrophilic, then very much compatible. If it is hydrophobic, means it is not compatible with the tissues, because our tissues are very much liking the water, isn't it? So that way, whatever the properties are there, we have to find out in such a way that it should be very much supporting for the properties when it is implanted into the body. And likewise, the functional groups also should be there, and the FTIR is done for that. So likewise, contact angle measurement, FTSCM, FTIR is the very general characterization processes that you may have to run for all the different samples. So here we were successfully able to make the hydrogels out of the axial membrane with the sol-gel methods, and the data is also published, and it was also showing a good cell culture over it. So it is compatible. Why compatible? Now the thing is that how we can go for more detailed way so that we can defend that it can be used for the bone regeneration. So likewise, the different hydrolyzed form was also there, and here we can see that we were successfully able to make the different thin films out of this material only. Likewise, the different characterization were also done. Likewise, cell study in vitro was also done, and our challenge was that ultimately whatever we are doing, we are using some kind of very harsh chemicals to digest it, isn't it? Actually, if we could able to find some solution so that it can be solubilized completely without using some kind of very harsh chemicals, so then we approached for the ionic liquids, and we were successfully able to find few ionic liquids. They were able to dissolve it completely. So we have another patent for this that is already granted, and if we are able to successfully dissolve it, now the complete open area is opening for its application. So likewise, Dr. Naveen was also talking about, okay, so here these ionic liquids are very much conducting, isn't it? So in that direction also some further advancements can be possible. So another is the hydroxyapatite. So another, what is the mechanism? Obviously, it requires very detailed discussions, but ultimately, whatever the material you are using it is osteoconductive, osteoinductive, so that osteointegration is very much supportive. Right? Osteointegration is what actually the biomaterials, whatever you are implanting into the body, it should integrate with the natural tissues, and more it is easier, more it is supporting for the regeneration. So in that, hydroxyapatite is very much supporting. So now let's come that what is the source of the hydroxyapatite? Right. So already we were engaged with the axials. So we started with the hydroxyapatite from the same source, and we were able to get it with this ball milling additional process, and we were able to get it in the nanocells. Right. And we were getting in the scaffold form also. Our priority was initially to get the 3D scaffold, whether it is able to, we are able to make it or not. Then after lastly it will come that how we are getting it in the 3D printing way. So other sources were also utilized in that. Piece scale was also there in our lab. Crab cells also we have utilized. So the same way with the similar calculations, we were able to get a wide range of hydroxyapatite from the different sources, and those were in the nano range also, right? With the different elemental analysis, XRD, we were able to defend that what we are getting, either it is the hydroxyapatite or beta TCP, or it is in the biphasic form. Whether either of these phases, it is very much osteoinductive. So this way, now the time has come that if we want to go for the 3D printing, hydroxyapatite alone is very difficult to print it. We have to put something, some polymers into it, right? So that flexibility we can introduce in the system. So for that, why not to start with the XL membrane and the XLs? Ultimately, what we are doing, it was the same cuticle layer that we were extracting from the egg initially, and we had isolated these two parts, modified it, converted it, and again we are combining it. Means ultimately that XL we are regenerating in the different forms. So here we had the XL membrane, right? Here the different functional, different groups were made with the different hydrogens, so that we can define that which is having the more pore size or the percentage or the surface area, because our defense system is based on that how the surface is working, how the functional groups are working, how is the porosity, what is the pore architecture. So based on all this, actually ultimately we can shortlist only few sample groups that we are further proceeding for animal cell culture or further biodegradability test. So here we can see that biodegradation can also be checked, and it was taking a very, initially it was very faster, but later on it was decreased to very slow rate. So likewise, tensile strength is also important because we are going to deal with the bone tissues, right? So based on the tissue, accordingly we have to check that what property we need and whether it is showing or not. If it is the bone, obviously we have to check that loading capacity is there or not, tensile strength is there or not. But if it is for the skin, we are more concerned for the elasticity rather than load bearing capacity, right? So based on all these applications, we have to find out that which sample groups actually we can proceed with. So here already we have seen that in vitro is also supported with these functional groups. So it was also implanted in vivo, and we were able to see that it was the hemolysis, because when we are implanting, the first reaction that it is dealing with the hemolysis. If it is not supporting, the hemolysis will occur, and that is not good for your body, right? So when it was implanted into the animal model, mouse model, so it was seen that they are least affected for the hemolysis. So if hemolysis is not happening, it means it can be further continued. So likewise, this in vivo studies was also done, and the histopathology was done, and our purpose is that we have to find out that in the control system, when we are actually taking out the tissue or damaging the tissue to make that model, ultimately after when we are implanting it, after maybe 6 months, what is the situation of that tissue, whether it is completely natural or still some damaged part is visible. So based on that, your success relies. So if it is completely natural one, you can tell that it can affect completely. Now let's come to another source also we tried, that is the fungus catfish derived hydroxyapatite. The calculation was similar, and we tried for the this 1.67 molar calcium to phosphate molar ratio. So that was the calculation that was made for it. Ultimately, the similar way we tried to make the scaffolds. The source, this time the source was different. Likewise, XRD, FTIR, and the biocompatibility was also supporting. Likewise, we also tried with the Arjuna terminalia graphite. So firstly, we derived the graphite from Arjuna terminalia. You might be knowing about this tree, very famous in ancient medicine. So the surprising fact about this thing, that if the similar methodology we tried with another source, the result was far away. Kind of means something is there in this composition of this Arjuna terminalia, that ultimately when we are making the graphite out of it, some extra factor is very much supportive for the cells, right? And another thing was that for graphite, if we are getting commercially from other sources, their concentration should be very, very less. Otherwise, it is going to cause cancer, means it could be carcinogenic. It is not supporting in our body. But when we are getting from this source, we can go for much higher concentration. We have tried it. So this is also published in Additive journals. So ultimately, firstly, we try to get the graphite, then graphene oxide, then reduced graphene oxide, and further we talked with the manganese also. So all the different sample groups were there, and it were very much supporting for the cell growth. So all these characterizations are done just to justify that what kind of material we are getting here and what kind of functional groups it is having. And here we can see that completely cells are completely alive. So very few in counts only the cells were there. So it was very much supporting for our study. So likewise, dermal toxicity was also done with this material. And here I was talking about the cellulose.
5 minutes.
5 minutes. So likewise.
3D printing still you did not started.
So I am directly going to 3D printing.
Yeah, that is
okay. So likewise, I tried with a variety of materials to get the materials of polymers so that we can make it the processing. Now the thing is that if we are able to get and define the polymer, next stage is that it has to be printed in 3D. But before getting into 3D printing, we have to define that what is the property of the polymer that I was talking about till now, right? When we are going to print it, many factors or properties are important. For example, the viscosity. It is very important for the polymers. Like if it is not there, whatever the biomaterials we have got it, if it is not there, then how we can process it, how we can modify it, how we can engineer it, how we can make the composite out of it is very important. That's why I was a bit discussing about its property, how it could further go for. So I'm just skipping all this. Now let's go with this. So here, if we talk about the materials, the varieties of materials that could be used to make the ink for 3D printing, right? And in this bio-ink formulations, all these are the components. But we have to see some factors, some properties that is very important, like bioprintability, and this is not a single word. Behind it, so many words are there. So for bioprinting, we have to see that how much viscosity is required for it. Maybe it may differ from model to model. The model that you have purchased may require a different viscosity rather than what I am using. So likewise, here thinning is also important for that, because while printing it, if the thinning is not optimized, ultimately it can affect that how the layer, over layer is getting printed. Likewise, degradation is important, because when you are printing it, that time it is printed, but slowly when it is coming into the systems, it may completely degrade it. So what is the degradability of the material that I was talking about in the beginning? How it is important, you have to study the biodegradation study. And out of a variety of a group of samples, you have to shortlist very few that actually you require for that particular biodegradation. Likewise, it should be supporting for cell viability that I was talking about, because directly you can't directly taking it and printing it. Some preliminary studies are also important to defend that it is the biodegradation and the cell viability that can support your 3D printing. So likewise, safe fidelity when you are going to print it at that time, I am also going to discuss with the video. So ultimately, all these factors are deciding that what is the printability of this. So this way, it is going to print layer wise. This is the extrusion based bioprinter, and here you can see that the 3D structure is made. After that, you have to go for the characterizations, right? But here one more thing is the stimuli. So if this 3D structure is able to affected by the physical or chemical or biological factors, and it is changing its shape in another dimensions with the due course of time, you can tell that some shape deformation is happening, and 4D printing you are able to do that. And why it is important 4D? Because many times what happens that what the pH that you have made for the 3D print, whatever the structure is there, when you are implanting into the body, the pH is affecting its structure, right? Many times it is very much limiting for your applications. For example, if it is not affected, what the shape you want, like for example this this shape you want. This shape only you have made in the lab, right? You are implanting it, and it is not affected by the pH. Then it is good. It is good for your application, right? But just imagine that with the effect of the pH, it is changing its shape. Like this, it has happened. You are assuming that it should go this way, but it has become this way. Then is it able to make your benefit? It is not in your code, right? So you have to make such 3D. When it is affected by the pH, it should get that shape. Getting it? Initially only you have made this 3D, affected by the pH, now it has become this, at this pH. So your purpose is fulfilled. So it is, you have to decide very intelligently that which shape it should be, and you have to try with a variety of shapes, and ultimately one or two shapes only will be successful at the end. So likewise, that approach is done. So likewise, so likewise, for how we go for the 3D printing, we have to get some data, medical data, and generally, if they are giving in DICOM format, that is good. If they are not giving, we have to convert in the DICOM format. Okay. Then again, that further we have generally they provide in DICOM format only, most of them, right? If they are not giving, then we have to, with the help of some software, we have to convert it. So conversion to NRDD format, then we are going to make in the STL format, and that STL format, when you are able to make it, you will be able to make it in the 3D print. You will be able to 3D print. The problem is that many softwares are available free of cost, the websites that you can utilize it. But when again you are going to make print it with your 3D printers, that some troubleshooting it will require. Okay. So case to case basis, based on the situation, we have to find out the solution. How this STL format that you have converted can be further printed. Okay. Ultimately, when it is going to the 3D printer system, it is able to 3D print. Okay. So likewise, this is one of the examples that how the data was taken. It was made in the 2D sectioning was done, and ultimately 3D format was done, and ultimately you can see that 3D model of it was, you were able to get it. Once it is, we are able to make it in a very finishing way. Okay, one thing is that how detailed this 3D architecture is, that it is important, right? For example, if you want to make an implant, so what bone part is damaged, exactly complementary to that you have to design it, right? And in that part, that designing is important. You have to learn that how to design in X, Y and Z axis very nicely so that it can closely mimic it, right? Now 3D scanners are also coming in market that can also directly be used. So once you are able to get it, one thing is that how detailed structure it is. Secondly, that what is the size of this, because it may not be compatible with your printer, right? So accordingly you have to resize it. Once it is resized, ultimately you can, this is the 3D printer that is going to print in that particular design. Okay, so likewise, so here one more thing, that this what you are able to see here is not good, not appealing, isn't it? So it is very important to know what not to do, isn't it? As compared means in the similar way what to do. So here, when you were able to print it, we tried it, and this way we were getting the structures. And what was the problem? The problem was that what the composition you have made was not having good viscosity. It was not homogeneous. And thirdly, since it was not homogeneous, time to time this nozzle was blocked. Right? Fourth, it was not making layer by layer. Before it was making another layer, it is still in the liquid form. So it was completely disturbed and distorted structures. Right? When slowly all these parts were resolved, ultimately we were able to get it very nice way, and this printed structures we were able to got it. Now the good thing about it, that this 3D printer we have made and designed in our lab only, right? And this designs what can be made with a 14 lakh instrument, we are able to make it in 30,000 price instrument that we are able to make.
30,000 rupees.
30,000 rupees, sir.
You can prepare that.
Yes, when I am making, I will send here also for your feedback. Yes, sir. I will send 2-3 IITs to some faculties. Their students will use it. And,
Did I see that when I went there? No?
sir,
When I went to your...
that time it was not ready. It was getting ready.
You told.
Yes.
So you patented this or not?
Till now, no.
Why not?
We'll see that.
People are selling at crores.
We need to modify it based on the feedback.
One
Once it is
crore.
modified, then we do.
Costing is only 30,000.
And here you see the comparison.
Needle size so big, huh?
Sir?
Needle
Uh,
so big. Micro needle.
yeah, micro needle is
No,
also
it is not
modified.
micro, it is maybe I think
This is
in millimeter scale.
millimeters.
Huh?
Other than that, we will also go for that. Okay, so likewise, we were able to also find out that the degradation and swelling, it is also important before we are going for the next stage. So likewise, we have done it. Cytotoxicity also in detail we did it with all the sample groups, we were able to got it. And here, this is the company that under which we, whatever the product our lab is developing, we are developing for commercialization purpose. And this is Electronics Engineering Private Limited. And this is the instrument that is also patented as well as in our lab, and that also one copy I am going to send to IITs for the feedback. So here I hope that who has already worked with the protein solutions for the using dialysis membranes so that they can purify it. So here so many restrictions if you are using it manually, these systems can automatically do it for you, right? And this also costing 50,000 only, right? So, here one book is there because most of the work that I am dealing with Excel only. So here one book is coming, Excel for biomedical applications, maybe very coming few months with the collaborator Professor Maxwell and Dr. Prof. And this is my research group. Obviously, whatever you can see in the slides, it is all the students and their effort that they have put forward. And we are the PhDs, MTechs, BTechs, all the project students who are working hard for getting some good research outputs. And this is my contacts. If you want in future for some queries or some collaborations, any kind of doubt that I can be helpful, you can have. Thank you.